Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be talking about photon energy. I'm going to be doing a couple of practice problems where the energy of a photon is involved. Either you're going to calculate it yourself, or you're going to use it to find a wavelength or some other characteristic. So in problem number one, we're given nitrogen gas laser pulse. So we're given a laser pulse of nitrogen gas, and we're told that it has a wavelength of 337 nanometers, and the pulse also has an energy of 3.83 millijoules. And they want to know what the number of photons are in this laser pulse. Okay, so the one thing I want to stress is that the equation we're going to use, which is the energy is equal to H nu, which is equal to Hc over lambda. And remember, H is the Planck's constant. And this energy, the important thing about this energy is this is the energy of a photon, a single photon. So to distinguish that, to make that clearer, a lot of times you'll see the word photon written there. So the energy of a photon. That's really important to keep in mind, that this is the equation where you're looking for the energy of the photon, or you're given the energy of the photon. Some students right away are going to be like 3.83 millijoules. Oh, I got energy. I'm going to put that here. But this is not the energy of a single photon. It is the energy of a laser pulse, which is many photons, right? So if you're going to use this equation, you first have to find the energy of the photon, right? So we're given the total energy of the laser pulse, right? We're trying to find the number of photons total. So in order to do that, you need to divide the total energy by the energy of one photon, and then you'll get your number of photons. So we got to use this equation to find the energy of a photon. And we're given here lambda. So we can use E, the energy of the photon, equals Hc over lambda, because we know Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds. We got meters per second. For speed of light, 3.00 times 10 to the 8 meters per second, and they gave us nanometers. So the first thing we want to do is convert nanometers to meters, because our speed of light is in meters. So 337 nanometers over 1. We know that 1 nanometer, I always put a 1 with the prefix, is going to be equal. Nanometer is going to be equal to meters. Nano means 10 to the negative 9. So I'm going to put 10 to the negative 9 with the base unit. So I'm going to use this. So 1 nanometer goes on the bottom, and then 10 to the negative 9 meters goes on top. So now I have meters. So if I do a calculation, so this is going to be this will end up being 3.37 times 10 to the negative 7 meters. Okay, so now I have my wavelength in meters. Now I just plug everything into this equation. So I have 6.626 times 10 to the negative 34 joule seconds, multiplied by the speed of light, 3.00 times 10 to the 8 meters per second, and then divided by my meters, my wavelength, 3.37 times 10 to the negative 7 meters. So seconds are going to cancel out. Meters are going to cancel out. I'm left with joules, which is the energy unit. So I'm going to calculate the joules. This will be the energy of a photon. So I have 6.626 times 10 to the negative 34 times 3.00 times 10 to the 8 divided by 3.37 times 10 to the negative 7 equals, and I get 5.8985 times 10 to the negative 19 joules. Okay, so keeping track of my sig figs, I have 4 sig figs here, 3 sig figs here, 3. So I'm going to have 3 as my last one. I need to convert millijoules to joules. So my total energy is going to be converted. So 3.83 millijoules over 1. 1 millijoule is equal to 10 to the negative 3 joules, right? So 1 with the prefix, 10 to the negative 3, the prefix multiplier with the base unit. Okay, so I'm going to put millijoules on the bottom. So 1 millijoule on the bottom, 10 to the negative 3 joules on top. Millijoules cancel out. I do my calculation. So this is going to be 0.00383 joules, and that's the total amount of joules. So now to find the total number of photons in the laser pulse, I take the total amount and I divide it by the joules per photon. This is joules per 1 photon. Okay, so the number of photons I'm going to divide by this. So this will be 5.8985 times 10 to the negative 19 joules per photon. Right, so I'm dividing those. Remember, I have 3 sig figs. I'm going to keep that 3. I have 3 here. So my answer is going to be in 3. Joules are going to cancel out, leaving me with photons, which is what I want. So I do the calculation. So then 0.00383 divided by that answer, and then I get 6.493 times 10 to the 15 photons. So I'm only allowed 3 sig figs, so I stop at the 9. So it'll be 6.49 times 10 to the 15 photons. That's the total number of photons in this energy, this laser pulse. Okay, great. That's the first problem. The second problem is I'm giving energy. It's told that the energy required to dislodge electrons from sodium metal is 275 kilojoules per mole. That's the total amount of energy. That's the energy that's needed to require to eject electrons. Okay, then they're asking what is the wavelength of light, and they want this in nanometers. Has a sufficient energy per photon to dislodge an electron from sodium. So we want the wavelength of a light that has the energy per photon. So per photon means that we need to find this. We need to find the energy of this. So that we could use this equation to find the wavelength, right? So we need the energy per photon. So we're going to use this. This is the energy per mole, right? This is energy kilojoules per mole. Per mole of what? This is per mole of photons. So we don't want moles of photons. We want per photon. So we're going to do 275 kilojoules over 1 mole. We want joules, right? Because if we're using this, remember Planck's constant is joules seconds. So we need to convert kilojoules to joules, and we need to convert moles to numbers of photons. So we're going to do 2 conversions. So we're going to convert kilojoules to joules. Remember, 1 kilojoule, again the 1 goes with the prefix unit, and then the prefix multiplier, 10 to the third, goes with the base unit. So 1 kilojoule is on the bottom, 10 to the third joules is on top. Kilojoules cancel out. Now I have joules. Awesome. Now I want to convert moles to particles. So 1 mole, I'm going to use Avogadro's number. So Avogadro's number is going to be used. So 1 mole of photons is equal to 6.022 times 10 to the 23rd photons. Okay, so moles of photons cancel out with moles of photons. Now I have joules per photon. Okay, so now all I need to do is calculate on my calculator. So I have 275 times 1,000 divided by 6.022 times 10 to the 23rd equals, and this gives me joules per photon, which it seems right, 4.5665 times 10 to the negative 19 joules per photon. That seems to be the correct magnitude. So now we have the energy per photon. Now we can use this equation here. So we're going to use this equation. So the energy per photon is equal to 4.5665 times 10 to the negative 19 joules. And that's going to be equal to hc over lambda, right? So hc over lambda. And then we want to solve for lambda. So when we solve for lambda, this we're going to multiply and divide. So lambda, right? Multiply both sides by lambda, right? So that cancels out. Divide by 4.5665 times 10 to the negative 19 joules, right? Divide that on this side too. 4.5665 times 10 to the negative 19 joules. So that'll cancel out. So then what you get is lambda is equal to hc, but h is 6.626 times 10 to the negative 19 joule seconds. C is 3.00 times 10 to the 8 meters per second. And then we're going to divide by this number here, which is our E. So 4.5665 times 10 to the negative 19 joules. Okay, so then when we put this into our calculator, we get 6.626 exponent negative 34 times 3 times 8 divided by equals, and then we get a large number or a very small number, so it's going to be 0 point, and then we got like 6 zeros, 435, and this is going to be meters, and then that's going to be equal 435 nanometers for the wavelength. So I hope you enjoy.